For step 3, we compute the test statistic. The test statistic for the one sample t-test is given by the following, okay? It looks really pretty similar to the z-test statistic. It's the point estimate, it's the sample mean, minus the claimed value of the population mean divided by the standard error, where the standard error is again the population standard deviation, divided by the square root of the sample size. This is sometimes called the t-test statistic. This t-test statistic, it lies on the t-distribution governed by n-1 degrees of freedom, where n is the sample size. So effectively, the shape of the t-distribution and the location of that t-test statistic on that distribution depends on the sample size. With a smaller sample size, the tails get a little bit fatter. And that's a more realistic model for the sampling distribution. So with a smaller sample size, we expect those sample means to bounce around a lot more. When the sample size gets larger and larger, the t-distribution looks more and more like the normal distribution. And in that, just reflecting the fact that we are more comfortable with using a standard normal distribution with larger samples as a model for the sampling distribution. And again, the t-test statistic, it just tells us how far a sample mean x bar is from the claimed value of the population mean of the null hypothesis. The more extreme the t-test statistic, the more inconsistent our data is with that null hypothesis, and the more likely we are to actually reject that null hypothesis under some given level of alpha. So let's examine t-test statistics. Right? The t-test statistic, it just tells us how many standard deviations our sample mean is above the claimed population mean, or how many standard deviations our sample mean is below the claimed population mean. Right? But the important point is that with the t-distribution, the tails are fatter to take into account our sample size. Right? So let's examine this sort of t-test statistics with this example of, suppose we just calculate a t-test statistic of 2.10. Let's visualize this. Let's understand what's going on. So the important point is that the location of the t-test statistic in the t-distribution is going to change depending on the size of the sample. This is in contrast to the standard normal distribution, where that z-test statistic, it has that same location on the standard normal distribution, because the standard normal distribution, it doesn't change depending on the sample size. This is why we need statistical software usually to calculate probability values and critical values with the t-distribution, because the location of the t-test statistic on the t-distribution, it changes depending on the sample size. So here's the t-test statistic of 2.1 on the t-distribution based on a sample size of 3. So the idea is, suppose we calculated a sample mean based on 3 respondents or 3 elements from a population. Then we'd expect the sampling distribution of that sample mean to look roughly like this. Right? The tails are a little bit fatter here. It's symmetric, it's mound-shaped, but it does not have the shape of the standard normal distribution. And we can see our t-test statistic lies right about here. Okay? With a sample size of 5, you can see that the distribution looks a little bit more normal. Right? This is just reflecting the fact that as the sample size increases, right, that sampling distribution is going to look more and more normal. Here's the t-distribution with a sample size of 10. And here's the t-distribution with a sample size of 30. As I said before, really with a larger sample size, as a rule of thumb, 30 or more observations by which you calculate your sample mean, that's a pretty large, relatively large sample. The t-distribution looks pretty normal with a sample size of 30 and above. But in fact, there is a slight difference, but it looks pretty normal. And so in this case, you can see that the probability of a t-test statistic greater than 2.1, for example, it's similar to what we'd find from a normal distribution, right? So we can compare that. Here's the standard normal distribution. So suppose we had a z-test statistic of 2.1. That probability, above and below that z-test statistic, it's very similar to with the t-distribution. Again, this just reflects the fact that the t-distribution approximates more and more the normal distribution with a larger sample size. And with that, we're going to go through a few examples of working through t-test statistics and really understanding what they tell us.